Okay, let's get going here. Sorry if it's a little warm in here. I have no control over it. The temperature currently right now is 80 degrees, but the thermostat is set at 67. So hopefully this will start working. This warm weather in this class reminds me of my second day ever that I was teaching. This was August 1994 at Kansas State University, my first year at grad school, my first course that I ever had. And it was 100 degrees outside, and the air conditioner did not work. Wow. But I made sure, and I kept the students there the entire time. So we will not be getting out early here today. I'm sorry. Okay, so the first thing I'd like you to do is I want all of you to log on to the computers and check what is the version of R that's on the computers, just to verify what you guys did on Monday worked. So, in order to log into, or in order to log in, use your my.unl login and password, or equivalently your Blackboard login and password. In order to access R, I believe you have to actually go to the Start button in the lower left-hand corner of your screen. And you can, it might actually say the version of R right there, or you might actually have to open it up. So, for example, on my computer, you can see I have a whole bunch of different versions of R on my computer. And we're looking for R 3.0.1. It doesn't matter if it says x64 or i386. The i386 means it's 32-bit. The x64 means it is 64-bit. If you open it up, if you have to open it up and look, the main thing is to look at the top of the screen. What does it say? Does it say R 3.0.1? If it does, you are good to go. I'll give you a few minutes to do that. Yes?
How imperative is it to have the latest version of R? So on my computer, I have like 2.1.4.
Ooh.
It's old. I guess
where you perhaps could come into problems with that old of a version of R is when you install some packages, it may not work as you would hope. So I recommend, if you're that old, I recommend updating.
You just delete it and then add a new one?
You don't even have to delete it. Just go to the R website, and download it from there. As you can see on my computer, I often just leave the old versions on there. But yeah, if it's that old, I would update. So, anybody have problems finding R or checking it out? Is everyone at the most current version? Okay, good. Also just as a reminder, remember you'll be using these computers here to take the test. That will be in 1 week. Obviously then it will be to your best interest to make sure that you do spend maybe just 5 minutes on one of these computers just to familiarize yourself with where everything is and so that you know what's available to you. Obviously the most current version of R is available. R Studio is available. TIN is available as well, the older version of TIN that I use in class. So with that then, let's take a look at the schedule, see where we are at. Again, the test will be in 1 week. We will spend part of the class, a small part of the class, next time reviewing for the exam. So if you have any questions, please feel free to ask the questions at that time. Again, we'll be discussing a little bit more detail the format of the exam. And again, just to give you a little bit of an idea of what to expect. And also as a reminder, remember this is a closed book, closed note test, but you do have access to all of my old programs, or all the programs that are on my website, I should say. Are there any questions before we get started here? Okay. So we left off last time at about page 19, I think. We're just about ready to present what the mathematical formula is, or equation is, for a multivariate normal distribution. First of all, just some simple notation here. When you have a univariate normal distribution, meaning that you just have simply one random variable, x, and we can denote that x has a normal distribution symbolically by saying x tilde, meaning is distributed as a normal random variable with mean 0 and a variance of sigma squared. Or, I don't know why I put 0 there, mean of mu, let's say. Now, when we talk about it in the context of a multivariate normal, we basically use the same notation. Notice how x is bolded, meaning it's a random vector. And the little p that you see here, between the n and the parentheses, says, well, basically, what is the dimension of this random vector? It's p by 1. It's p variant, people would call it. So there are p random variables, a mean vector of mu, and a covariance matrix of sigma. With that, then, our actual mathematical formula for f of x with a multivariate normal is what's shown right here. For comparison purposes, let me write out what f of x would be for a univariate normal. Let me get a thinner tip to my pen here. That will help me not run out of room. There we go. Okay, so hopefully you can read that. I don't have the best handwriting in the world. So that's the univariate normal. Now let's compare it to the multivariate normal. So I have a square root of 2 pi here for the univariate, meaning 2 pi raised to the 1 over 2 power. Notice now what happens. I have 2 pi raised to the p divided by 2 power. The sigma squared, or I'm sorry, the sigma part that you see there, that's like sigma squared to the 1/2 power, essentially. Notice what happens in the multivariate normal. I take the determinant of my covariance matrix and I raise it to the 1/2 power. So you see some similarities, obviously. And then we have the exponential function. We have a negative 1/2 out in front, a negative 1/2 out in front. Notice how I'm squaring x minus mu for the univariate. So it's like taking x minus mu times x minus mu. Well, the equivalent in a multivariate setting would be then to take x minus mu transpose times x minus mu, essentially. And then notice here I'm dividing by sigma squared. Well, now we are taking the inverse of the covariance matrix. And just verify to yourself that for a multivariate normal, if p was equal to 1, if you use that equation, you get what you would get for a univariate setting. Obviously, we need to make sure that our determinant is greater than 0 for sigma. Otherwise, we're going to have some difficulties finding f of x. Okay, so let's look at a plot of what this multivariate normal distribution would look like in a simple case where p is equal to 2. We call this the bivariate normal, bi meaning 2. So x, my x vector in this case, has x1 and x2. Let's just set, just so I have some values for them, let's set mu to be a 15 and 20. And then here's my covariance matrix. So for example, 1 is the variance of x1. 1.25 is the variance of x2. And 0.5 is the covariance of x1 and x2. Again, covariance matrix is symmetric, so that's why you see 0.5 on that other portion. So this means I have positive association between x1 and x2. In other words, as x1 increases, I expect x2 to increase as well, on average. Symbolically, we could denote all this by saying x is distributed as, and then just put in what mu and sigma is into this normal distribution format. Okay. Well, what's the correlation matrix then? Remember, if I have covariance matrix, that means I can get the correlation matrix. So simply, the correlation between x1 and x2 is you take your covariance of x1 and x2, and you take it divided by the square root of the variance of x1 times the variance of x2. And so we get a correlation of 0.45. Again, correlations are between -1 and +1. So what this says is that I have kind of a moderate positive association between x1 and x2. Well, if you really, really wanted to, you could put mu and sigma into your mathematical expression for f of x, and that's what I did there, just mainly for demonstration purposes. I could have probably simplified it down a little bit further, like actually taking the inverse of this matrix. For some reason, I did not, but one could do that. And so this is the mathematical expression. And again, what this mathematical expression has given us is simply, you can say the height of our, instead of a curve, is going to be a surface. Because now we have x1, x2, f of x. So now we're in 3 dimensions. Let's look at then how we can plot this in 3 dimensions. To do the 3D plotting, we're going to use a package called RGL in R. This is a package that you would actually need to install on your computer. It's not there by default. RGL stands for R, as in the software package, G for graphics, L for library. Also, to do some stuff with the multivariate normal, we need to use the MVT norm package, multivariate normal. That's where the name comes from. And so what I'm going to do, let me actually jump on over here to 10. Oops, I forgot to make this bigger. Okay, so I'm going to create a vector, call it mu. It's going to be obviously my mu vector. I'm going to create my matrix sigma. Of course, remember how to create a matrix. You use a matrix function. For the data argument, you simply put in the elements of your matrix. I'm going to specify number of rows, number of columns, and then I don't know why I didn't need to do this. I said by row equal true. So what does that mean? It's going to put the elements in by row into the matrix. Would I get the same thing here, though, if I said by row equal false? Yes, because remember, covariance matrix is always symmetric. So it actually doesn't matter what I do here. I think it's just more out of habit. I think of putting stuff in by rows first versus columns. And so by habit, I just put that in there. There's a nice little function R called cov2core, which actually automatically calculates the correlation matrix for you. So for the argument V, you can put in sigma. V, probably the reason why V is used because some people call covariance matrices variance dash covariance matrices. So that's probably where the name comes from. And you can automatically then calculate your correlation matrix P. Really easy. Okay. Now, if you remember last time we looked at a function called d norm that allowed you to calculate f of x for a univariate normal distribution. For the multivariate case, there's a function called dmv norm, and it works in a very similar way where you have to specify what your mean vector is and what your covariance matrix is. I'm going to evaluate my f of x simply at mu. I could have chose some other value. I just decided to choose at mu, and it's going to be 0.159. Similar to the univariate normal case, the highest portion in the univariate normal case, highest portion of your curve, remember, was when x was equal to mu. Same thing is going to happen here, but again, it's just going to be a surface. It's going to be in 3 dimensions. Okay. Now, previously, to do the plot of the univariate normal, we simply used the curve function. So you gave the mathematical expression for f of x, and you said, R, go plot. Unfortunately, there's not a good there's not a good curve function, curve-like function that could be used when you're graphing in 3 dimensions. So what we're going to have to do instead is decide on some x1 values, decide on some x2 values, plug them into our f of x, evaluate, and so that what we're going to have is a grid essentially of a whole bunch of x1, x2, and f of x values, and then we simply tell our plot them. Okay, somewhat, this is maybe, the first time you ever plotted a 3D, maybe like in a junior high setting, this is what you would have done. Okay, so I'm going to create a sequence of numbers from 11 to 19 by 0.1 for x1. Why did I choose that? Well, remember, x1 is going to have a mean of 15. And so what I thought, okay, I'm going to go, I guess, about, in this case, I went 4 standard deviations from the mean, just to make sure that I'm going to capture everything in my plot. And I decided to go, I guess, by 0.1, just to make sure I have a whole bunch of points that I'm evaluating at. x2, 17 to 23. Remember, the mean of x2 was 20. And let me actually just go ahead and run that, just so that you can see, indeed, there's x1, and there's x2. Okay. Now what I like to do is come up with all possible combinations of x1 and x2 that I could have here for all these numbers. So to do that, there is a function called expand.grid. If I say expand.grid x1, comma x2, put then an object called all.x, you can see what's starting to happen. For x2, which is represented by the second column, I have a whole bunch of 17 values corresponding to the first value for x2. And then x1 is going to vary corresponding to all the possible values of x2. If I want to see the bottom of the all.x data frame, I can use the function tail, and you can see how the last value of x2 here, 23, and then for x1, I'm going through all the different values. So you can see I have 4,941 different x1, x2 combinations. Now I want to evaluate f of x for each of them so I can plot this. Are there any questions so far? Okay. So to do the evaluation, I simply use DMV norm, as we just saw. I put in for my x argument all.x. Now R recognizes, okay, you have this big data frame here, so what it's going to do is for one row at a time, evaluate what f of x would be corresponding to elements of x1 and x2. So when x1 is 11, x2 is 17, f of x is 3.24 times 10 to the negative 5th power. When x1 is 11.1 and x2 is 17, I get 4.56 times 10 to the negative 5th power. Okay. So essentially, to graph this in 3D, I have something now for my x-axis, something now for my y-axis, and now something for my z-axis. But I need to arrange the values for the z-axis in a particular way to correspond to how R's functions work. And this is how I need to arrange these values for the z-axis. I need to put all these f of x values into a matrix, where the elements inside the matrix are the f of x value for corresponding x1 and x2. So for example, the 1, 1 element of the matrix corresponds to when x1 is 11 and x2 is 17. The 1, 2 element is going to be x1, 11, x2, 17.1. I just need to rearrange this stuff. Right now, just to make sure you see this in case it wasn't obvious, we can see that this eval f of x is just a single vector in R's terminology. I need to put this all into a matrix in a particular structure. So to do that, I use my matrix function, I put in my f of x values. How many rows do I want? Well, same number of rows as what I have for x1. Number of columns, same as in x2. I'm going to do by row equal false in this particular case, just because it was a little bit easier to arrange the stuff. And so that if I did f of x, we'll look at the first 25 elements in it. And you can see now everything's arranged in a matrix-like structure. On your own, you should go through this code here to verify that indeed that I did arrange stuff as I had intended up there. Okay. Now finally, after all that work, we can actually do the plot. This function pers3D stands for perspective 3D. It's in the RGL package. This is how it works. The x-axis corresponds to my x1. Y-axis corresponds to x2. Remember, these are sequences of numbers. This z-axis corresponds to this matrix f of x. I want this surface that's going to be plotted to be green, just to make it look pretty. I have some nice x-axis, y-axis, z-axis labels, and also I put some limits on my x and y axes. I could have done that for z too, I just decided not to. This is what I get. Okay. Notice how I have a new plotting window pop up. This isn't the standard R graphics window like what we've seen in the past. It's actually uses some Java code to generate this. So I'm just going to make this a little bit bigger. And so this is what the multivariate normal looks like. To help you see this better, and the reason why I think this package is the best of the 3D packages in R, is that I can actually rotate this plot. So if I just left-click someplace in my plot here, hold down my left mouse, and then just drag, you can see me be able to rotate what's actually shown there. And so this helps you give you some perspective of what exactly this distribution is showing. Again, this is a probability distribution. So the volume underneath this surface that you see is what? 1. Okay? Just like the area underneath a curve for a univariate is 1. Now we are talking about volume. You can see, depending upon the angle you're at here, you can see, for example, where is that? There it is. So I have a problem seeing where x2 was. So the x1 axis goes from 10 to 20. The x2 axis goes from about 15 to 24. That's what was specified in my call to my function. You might be wondering, why don't you see this green extend all the way to the edge of the plot? Well, just remember, I didn't necessarily evaluate x1. I did not evaluate f of x at x1 between, I did not evaluate f of x at all these values of x1 and x2 that I had actually drawn the plot for. Look at the x-axis, y-axis limits, and compare to when I said x1 gets sequence, SEQ, or x2 gets a sequence. Okay, so you can do a whole bunch of things. You can even look underneath. I don't know why you would want to, but you can. So, you know, it can be helpful just to see it. Notice also here how the, move this up. Notice here also that that there appears to be more variability in x2 than there is for x1. In terms of it's a little bit wider for x2, the surface, than it is for x1. Why is that? Yeah, perhaps that was too easy, but you remember what the variance for x2 was 1.25. The variance for x1 was 1. So that's why you see that. Let's see what else I wanted to discuss. If you really wanted to, too, you can zoom in and zoom out on one of these plots. The way that you do that is use your right mouse button. You click and hold, and then, whoa! Yeah, I'll do this a few times. Anyway, you can zoom in, zoom out by then just moving your mouse when you have the right mouse button pressed on. Okay, so that's one way that we can plot our multivariate normal distribution. Another way is to use what's called a contour plot. I would imagine that all of you have seen contour plots before, maybe not in a statistical context, but you have seen a contour plot with respect to, let's say, a map that shows elevations. So, for example, maybe I have some kind of map here of a piece of land, and you might see some squiggly line like this, another squiggly line like this, another squiggly line like this. And this might be, let's say, an elevation of 20 feet, 30 feet, 40 feet. So everywhere on that line, if you think of a map, everywhere on that line, if you were standing there, you'd be at an elevation of 20 feet. The next line 30 feet, next line 40 feet. Well, we can essentially do exactly the same thing now, but in the context of plotting a probability distribution. So I want to know, for example, where is this surface at f of x equal to 0.14? Where is it for f of x equal to 0.12? And so on. And so essentially here, so we have some additional coding here. I'm going to run real quick. You can look at this code on your own. It's the perspective function, and what I'm going to do is draw a little plane in the space. So this is at f of x equal to 0.12. And so you can see where it intersects my my surface here, and if I look at it from above, as much as I can here, if you think of it in 2 dimensions, what shape is that? It's a ellipse. Okay. So that is for f of x equal to 0.12, I could do exactly the same plot for f of x equal to 0.14. Of course, that's going to take me a little bit higher up. So that gives you some perspective of where I'm at. And then if I look at it from above again, now you have an ellipse as well, but now it's a smaller ellipse. So essentially what a contour plot does in a statistical context is it takes all these ellipses and plots them in 2 dimensions. So let's take a look at the plot of page 1.22, and I'll describe how that comes about shortly. So here's a contour plot now of this bivariate normal distribution. And you can again see where these lines are. I know it's a little bit small here. Let me see if I can blow this up a little bit. So for example, at the contour of 0.14, this represents where f of x is equal to 0.14. So if I kind of project down here to where I have my x1 axis and project over for my x2 axis, you can see when x1 is maybe about 14.5 and x2 is maybe about 19.5, I will get f of x equal to 0.14. Also in a similar manner, I could come over here and touch the line again. Maybe I'm at 15.5 for x1 and I'm at 20 for x2. This is another point where f of x is equal to 0.14. Okay. So again, this is showing us the heights of the curves. Oh, not the curves, the surface. Here's a question. If I were to take a sample from a population that's characterized by this bivariate normal, and if I were to do a scatter plot on top of this, where would you expect most of the points to fall? Would you expect points to fall out here? Or would you expect points to fall maybe in there? In the middle. Why? That's where I have the highest probabilities. So if I were to take a sample from, again, a population characterized by that distribution, I might see something like this. And it's hard for me to represent this here, but you would expect the intensity, let's say, of the points to get higher as you go more towards the middle of those ellipses. As you get further out from the middle of those ellipses, the intensity of those points, or let's say the frequency of those points, would be less and less and less. Okay? Think of this in the context of a univariate normal distribution. If somebody told you, okay, here's my univariate normal distribution, where would you expect most of your sample to fall? Probably, right around here, where a higher intensity, more in the middle. Any questions about that? Well, why is this important to note? Well, we use probability distributions to help characterize real-life events, let's say, or real-world applications there. And so that's why you need to have an understanding of this particular kind of a probability distribution in a class setting. Also, I want to point out here is look at where the distribution is centered. You could do this on the 3D plot too. Where's the distribution centered? At the means. So remember, x1 had a mean of 15, x2 had a mean of 20. Remember, with a univariate normal, the distribution was centered at the mean. Let's talk about how we get this plot. While this wasn't necessary here, I decided to do this. I think we've maybe seen this option before, or this function before. PAR stands for graphics parameters. And I'm going to use a graphics parameter function to control what my plot's going to look like. In particular, I'm going to use the argument PTY for plot type with an argument value of S, means square. The default is M for maximum, meaning the plot will maximize the space that's available to you in the open window. Here I just want to have a square. I don't need to do it, I just decided to do it in this situation. To do the contour plot, first of all, this function exists in the regular old graphics package, which is automatically installed in R, so this is not in the RGL package. Contour, just specify what's on your x-axis, specify what's on your y-axis, specify what's on your z-axis. Remember, the z-axis value is actually a matrix. For those of you who've done contour plots in SAS or maybe 3D plots in SAS, you'll note that this is a little bit of a different format than what you've seen like in a proc G contour, I believe the function is called, or proc, I don't remember what for a three-dimensional plot, what it is in SAS. It might be proc G 3D. I'm sorry, did you? Okay. So I put a nice little title on my plot, nice labels for my x and y axes. I control what the x and y axis limits are. Here's my plot, and there you go. There's one little problem that I've noticed with the contour function R. I don't know why this occurs. Is that in order to do grid lines on this plot, on a plot like this, what we've done in the past is to use the panel.first is equal to grid argument. You'll see our introduction notes for an example of that. If you do that here, things don't work out quite right. So what I've done here is kind of manually drawn horizontal and vertical lines on my plot using a function called AB line. The H argument stands for horizontal line. The V argument stands for vertical line. And I generate a sequence of numbers from 16 to 24 by 2 for my horizontal lines. And then for vertical, 10 to 20 by 2. And you can see where my, now you can see grid lines there. Grid lines just are helpful to view a plot. Okay. Are there any questions? Temperature is still, it's up to 80.5 degrees now.
Can I ask a question?
Sure.
Back on page 20?
Okay.
Why is the square root of that variance matrix 1?
It's a determinant.
Oh. So it's not the square root of the matrix.
Yeah, so I got those vertical lines there. Yeah, sorry if that wasn't clear. It's the determinant. Take the determinant first.
Yeah.
Okay. Now, let's look at if we change some things with this multivariate normal. How does it affect these plots? Let's just make one simple change. Let's say I increase the variance of x2 to be 3. Now, without even plotting it, you should have some general ideas of what's going to happen. So don't look at my notes. Don't look at the plots there. What do you think is going to happen? Some ideas. There's going to be more variability in the x2 direction. Okay? Is the center going to change? No, just going to be more variability. What do you think is going to maybe happen to the height of the surface? Will it go up or down? It's going to go down because now you have a larger space where you need to still have a volume of 1 contained within inside it. So let's see what happens here. So then now also notice that the corresponding correlation, verify this on your own, drops down to 0.29. And to do these plots, so this is in my program again, well, I decided, so I'm talking too fast and I'm getting, it sometimes makes it difficult to talk. What I'm going to do first is do exactly the same plot that we saw before for the same distribution. It's just I'm going to control my x and y axis limits in a little bit different way so that the two plots are going to be exactly on the same scale. So look at the code on your own, just controlling my x and y axis limits. So this is exactly the same distribution that we saw at first. Now let's look at what happens when I change that variance. So here's the new sigma that I'm going to have. And I just basically essentially need to run the code again. Now you note that the surface is a lot lower than what it was before. In the x2 direction, it's more spread out than what it was before as well. Page 120, or I guess my notes are a little bit different from yours, but I think about maybe page 126 maybe of your notes, you see something like this. What page is it for you guys? 126, okay. I had printed off my notes a few weeks ago before I had made some additions to it, so that's why my page numbers are a little bit different from yours, at least my paper copy. But here's a nice little diagram showing the comparisons between the distributions. And again, the purpose here is for you to understand what these distributions are going to look like. Because again, we use these distributions to help model reality in the end. These distributions will be the underlying assumptions that we're going to make in order to do some of the statistical methods that we will have this semester. So again, notice the heights. The height has dropped here, centered at the same spot. It's a little bit more spread out. You can see that a little bit better with respect to the contour plot, the more spread out on the right side there. Also notice that the ellipses that you see there are rotating a little bit too. Any ideas why that might be happening? Well, we'll come back to that. And perhaps I went a little bit overboard, and you can look at my code in the program. I decided to actually overlay in 3 dimensions the two distributions, so you can see how the green one, which is the original distribution, is a little bit higher. But if you notice on the left and the right side here, you start seeing blues because you're more spread out than you were with the green. The blue is the second distribution. The green is the first distribution. And then you can even overlay the contour plots as well. I find graphing fun, and hopefully you will too. So let's talk about some questions about the bivariate normal in general. So what's going to happen with these plots as the mean changes? Essentially, you're just going to shift. So if I increase the mean for x1, you're just going to simply, and keep everything else the same, you're simply going to shift to the right. What happens if sigma 1, 2 is equal to 0? So that's the covariance. First of all, what would be the correlation?
0.
0. Okay. Now in your first stat course, you looked at a case like this where you had maybe an x and a y, and you looked at a sample that would maybe have a very low correlation. What would the sample look like if I were to draw a scatter plot of it? Essentially just kind of a random scattering of points here. Okay. and more points towards the middle if you're, let's say, simulating for a normal distribution. Essentially, yes. Now, if I were to draw contours on that, look what's going to happen. So what's happening here is that you're seeing that there's no association between, let's say, x1 and x2. And you see the effect then in the distributions with these contours kind of becoming more upright, I guess you could say. And so, then you should ask yourself, what do you think would happen if you had maybe a, I guess I have that eventually there, a perfect correlation? 45-degree angle. And the points are going to be very tightly clustered next to each other if you had points. What's going to happen to the contours? Very tightly together. So what I've done to help you investigate some of this stuff here is that you can see in my code here a whole bunch of, let's say, covariance matrices that are commented over. Well, run this code without one of those covariance matrices commented over and see the effect on the plots. So that will help you better understand what happens with a multivariate normal under different settings. And you don't have to necessarily go with my settings here. Go with some of your own. See what happens. Explore. What happens, let's say, if maybe you had negative correlation instead. Well, in your first stat course, if you had a negative correlation and you did a scatter plot of the data, you probably saw something that looked like this. Because as x goes up, y goes down. Well, how does that affect the multivariate normal? Okay. Are there any questions? Okay, well, let's say that you do take a sample from a population that has more than one variable, and you need to summarize that sample. In other words, calculate summary statistics. One of the first things that you do in your first stat course is you learn about how to calculate a sample mean, how to calculate a sample variance, and also interpret them. Well, let's now do the extension for a multivariate case. So let's let x1 through xn be a random sample from a population characterized by some kind of multivariate distribution. Notice I'm not necessarily saying normal. There are many, many multivariate distributions out there. It's just the normal is often the easiest to work with, and so that's why we focus on that more so in this course. But we know that there is some kind of mean vector. So in other words, the expected value of x1 is mu. Expected value of x2 is mu. Expected value of x sub n is mu. And also they all have the same covariance matrix as well. So the covariance of x1 is sigma. Covariance of x2 is sigma, and so on. We can denote, there's a variety of different ways to denote this kind of stuff symbolically. That's one. Often, generally speaking, it will be clear that indeed we do have a random sample of size n, so we might just simplify it and just say simply x is distributed mu sigma, where we're not specifying the particular distribution. So let's look at some summary statistics. The estimate of mu, we're going to call it mu hat. And as you might expect, just simply add up all those data vectors that you get that contain your observations. Add them all up, divide by your sample size. The covariance matrix then, let's actually think about in a univariate setting. Let's have sigma hat squared. Maybe in another class you've called it S squared for the sample variance. You would have 1 over n minus 1 times the sum I equal 1 to n, or let's actually use r, excuse me. The sum r equal 1 to n of x r minus, you would call it x bar. How about we just call it mu hat squared? Now we do the equivalent now in a multivariate setting, or a similar equivalent, where now we take xr minus mu hat times xr minus mu hat transpose. XR is going to be P by 1 in dimension. So what's going to be the dimension of my covariance matrix then? P by P. I have an n minus 1 here to essentially say, let's take a kind of an average value. Well, does anyone remember why you did n minus 1 for the regular old sample variance? Because it provides an unbiased estimate of the population variance. We essentially do the same thing here. So in fact, both mu hat and sigma hat are unbiased estimates of their corresponding population quantities. Okay, so some notes. This is probably obvious. The mu hat, simply what you could do also is just take the sample mean for every single variable, put them into a vector, voila, you have your mu hat. Sigma hat, this is, I guess, more for emphasis here. Just like sigma itself, the estimated variances for the corresponding variables are on the diagonal. So notice I'm putting a hat on top of the var to emphasize that this is an estimated variance, not an actual population variance. The off-diagonal elements then are the corresponding covariances, estimated covariances that is. Well, how do you find this estimated variance? Well, just like you did in your first stat course, and actually I had essentially just demonstrated before, except for maybe the notation might be a little bit different from your first stat course. So x sub ri, remember that is row R, column I of your data matrix. In other words, variable I, observation R. You subtract off the corresponding mean for that particular variable. Sample mean for that variable, you square it. Add them all up, divide by n minus 1. To find the estimated covariance, you may or may not have done this before. This is the corresponding formula that you would use. You actually all have done this before because it's used in calculating a sample correlation, since your professor may not have told you what this formula represented. Well, where does this formula come from? Well, you can think of it this way. Let me see here. Let me get some room. So remember what the covariance is. Covariance of x, let's do xi, xj is equal to the expected value of xi minus mu I, xj minus mu j. And so just like with the variance formula, when you're finding the expected value of xi minus mu I squared, essentially what you're doing here is that for the expected value part, that means take an average, you have the 1 over n minus 1, and you're averaging over all the different products that you see here, but now with sample quantities replacing the mu. Okay. Now there's actually another convenient way to calculate the covariance matrix that will actually pop up later in the semester. Let's let, again, our data matrix that we learned about last time was denoted by a bold letter X. How about we define something called X tilde? Exactly the same, except for I'm going to replace all the elements of my matrix with mean adjusted values. In other words, if this is my X tilde matrix, X 1, 1, I'm going to subtract off X bar 1. Or you can say mu hat 1 if you prefer. Meaning I'm going to take the first observation, first variable, subtract off the corresponding mean for that variable. X2, 1 minus X bar 1. And keep on going down. We'll do the second column too. X 1, 2, second variable, first observation, subtract off the second variable sample mean. And just keep on going down. So this is a matrix of mean adjusted values, mean adjusted data values. Then what one could do is show that sigma hat is actually equal to 1 over n minus 1 again, but you take x tilde transpose times x tilde, and you get your covariance matrix. On your own, try a very simple case, such as p equal 2, n equal 3, to see that indeed this is true. Actually program it into R if you want to see that it is true as well. Okay, so we have an estimate of mu, we have an estimate of sigma. Well, what about an estimate of p? P, again, is the correlation matrix. It has elements denoted by the Greek letter rho. Well, the corresponding estimates that the notation that we're going to use is capital R is going to estimate p. A little r sub ij is going to estimate little rho sub ij. So this is the, you can say, the sample correlation for variables xi and xj. To find the sample correlation, you use exactly the same formula that you saw in your very first stat course. Remember what the population correlation, how it's represented. It's the covariance of xi and xj divided by the square root of the variance of xi times the variance of xj. So what we do here is we put now then the estimated covariance in there, and we put in the two estimated variances. Some simplifications happen. So for example, the 1 over n minus 1s fall out. And this is actually probably the formula that you saw in your first stat course. Sometimes a professor will even go further and show you a little bit more computationally easy to calculate formula if you do it by hand. But this is the formula. We can put all these sample correlations then into a matrix structure, just like what we did with the correlations involving the population correlations. Okay, so let's apply this to a simple data set. This is with the serial data. If you remember, we have a sample of size 40. And to find then the sample means, or the mu hat vector, again, let me actually show you the data. Let me do a split screen here. Remember, we are using the serving, we're going to use the serving size adjusted values. Oh, where is it? There we go. So there's my data set. So we're going to just work with sugar, fat, and sodium this time. So for the sugar mean, you know, take 0.357 plus 0.0714 plus all the way down to what you see as 0.1. Take the mean of them and you get the average sugar content for these cereals. My pen is not working very well. Well, tablet PCs, they work very well, except for when you have split screens here. Fortunately, I never have figured out how to work properly when you do a split screen. Hold on. Okay, I want a yellow highlighter. There we go. So the mean sugar content is 0.2894. So about 29% of the per serving size is sugar for the cereals in our sample. For fat, 3.2%. And then for sodium, 5.6. Remember how we found that, or how we adjusted the data values there. We took the milligram value divided by the serving size gram value. So that's why that's not a percentage. To find then the covariance matrix, it's just a matter of plugging in all the different values for your observations, subtract off the corresponding mean vector, and do this 40 different times, add them all up, divide by 39, and eventually you get to your covariance matrix. For a sample size of 40, would I expect you to do this on a test? Do these calculations by hand on a test? Yes. No. Why am I doing it here? Just demonstrate the process. We will use R to do something like this, but you need to understand more than I use a function called cov, as you will see shortly, to do this calculation. Then here's the correlation matrix, and just as a reminder, this negative 0.1636 represents the correlation between sugar and sodium. How is this found? I took negative 0.0602 divided by the square root 0.0224 times 6.06. So do we have much association between these, between sugar, fat, and sodium here? No, not a whole lot. Remember that, because that will be important later when we do some other stuff with this data set. There's not really a whole lot of association going on here. Okay, so how do I do this stuff in R? This would be the main way that we do this. Let me bring up my serial program. I'm going to read in my data. My data is stored in an Excel file. I'm going to use the RLDBC package. Again, if you have problems using this package, just simply save the Excel file out as a comma delimited file and use the function read.table, or use a function also called read.csv for a comma delimited to read in the data set. So just to verify that indeed that I did read it in correctly, I usually use like the head function to look at my data that I read in. I'll look at the tail function as well to look at the last 6 observations. Now I need to adjust my data, and this was actually a question that we had, I think, yesterday. How do you adjust your data so that it is per serving size? Very simple. Inside my serial data set, there is a variable called sugar_G, which gives me the number of grams of sugar per serving size. Just to show you that. There's my data. So 10 was the very first one. There's the 10 right there in the data set. And I simply say divide by a variable called size_G in the data set, which contains the serving size. So the first serving size was 28. That was for my Kellogg's Razzle Dazzle Rice Krispies. So when I divide them, this is what I get. So the first cereal was 0.3571. 35% of it was sugar content. Well, how do I put this into a data frame using R's terminology? How do I do that? It's not too difficult. I'm going to create a new variable called simply sugar. And I'm going to say serial $sugar gets the results from doing this adjustment. So if I now do head serial, you will see there's a new variable in there called sugar. Any questions about that? There's a variety of different ways that you can get a new variable in a data set or data frame. This is just the way that I chose. So if you've seen something else in another class, that's fine to use that too. I'm going to do the same thing for fat and sodium. So that in the end, this is what my data set looks like. Okay. Now let's do some summary statistics. I want to find the estimated covariance matrix involving sugar, fat, and sodium. The function R that allows you to do that is the cov function. Now, the easiest way to do this is just simply specify the particular variables in your data set. In this case, the 8th variable, the 9th variable, and the 10th variable contain my sugar, fat, and sodium content. So what I could do is this. Look at your serial data set, take all the rows, but just take columns 8, 9, and 10. And if you notice, there's sugar, fat, and sodium. I'm going to use then the co-function with that to find the estimated covariance matrix, and then this matches what we had before. And you can put the results into an object called sigma.hat. So we can maybe use it later for some purposes. Another way that I could have specified this was to say 8:10. I think we've looked at this before. If not, let me explain it. The colon basically allows you to generate a sequence of numbers, but in this case just into integers. So 8, 9, and 10. To find my correlation matrix, one way I could have used was to use the core function. Put the results into an object called R, and there's my correlation matrix. Alternatively, I could use that cov2 core function that we saw earlier with the covariance matrix and get exactly the same thing. Okay, well, what about then mu hat? So my estimated means. Again, there's a variety of different ways that one could find these. What I think is the simplest way is to use a function called call means, column means. So by columns of your data frame, find the means. So do that then with my serial data, put the results into mu.hat, and there we go. Another way that you could have done this, and this function will be more useful later in the semester, but we can talk about it now as a simple introduction, is to use a function called apply, which allows you to apply any kind of other function that you want by columns or by rows in a data frame. So I say apply, my x argument says, well, where's my data? It's right there. Margin says, do I want to apply by columns or rows? The value of 2 corresponds to columns, the value of 1 corresponds to rows. Look at the help for the function, you'll see that. Then what function do I want to apply to every column? So fun equal, I want to apply the mean function. Mean finds means. There you go.
Excuse me, sir?
Yeah.
Where are the code in the
Excuse me?
website? Where can I find the code?
Section materials webpage.
What was the name of that? Serial.org?
Serial.org. Yeah. Okay. So finding summary statistics is not the most interesting thing in the world, but it is a place that we need to start in this class to so that we can do more complex things later. Okay. Any questions? Any other questions? Let's go back to this bivariate normal distribution once again. And let's actually simulate a sample from this same bivariate normal distribution that we first started talking about. Let's look at how we can do this in R, and then also find some of these summary statistics. So again, X has a distribution that's multivariate normal, bivariate normal in particular. Here's my mean vector. Here's my covariance matrix. Okay, so I'm going to create my mean vector, create my covariance matrix like before, and let's say I want a sample size of 20. So I'm going to create an object called capital N. That's going to be 20. Now to simulate my data, I'm going to use an RMV norm function. R stands for random multivariate normal, just like R norm that I think we've seen before in this class for random normal. My sample size, capital N, corresponds to little n argument. I specify my mean vector and also my covariance matrix. Now I'm going to put this into an object called X, for the lack of a better name, Maybe I should use a capital X to mean that this is my data matrix. I just use a lowercase x. And there's my simulated data. So my first observation, x1 was 14.6, x2 was 18.8. Now if I were to run exactly the same code again, what's highlighted, will I get the same sample? Did I get the same sample? Nope. Okay, so I didn't get the same sample. Why not? Yeah, because this is randomly simulated data. So every time I run this code, I'm going to get a different sample. Well, how can we stop that from happening and always get exactly the same sample for, let's say, demonstration purposes? That's where we can set a seed number. We talked about that briefly before in this class. Hopefully, in your very first stat course, your professor was actually showing you about, telling you about random number generation, but sometimes that doesn't happen. And to guarantee that you always will get exactly the same sample, run right before RMV norm in this case, run the set.seed function. What a seed number tells R, or actually any kind of software package, it tells the software package essentially where to start when it's simulating the data, without going into all the details. Some stat departments will have a whole class on random number generation. Fortunately, I never took one of those because that sounds kind of boring. But essentially, this is what a seed number does. And what you need to get out of it, it allows you to simulate always exactly the same sample. So notice 15.99, 20.4. If I do it again, 15.99, 20.4.
How do you turn that off after you said?
Well, if you were to now only run this segment of code, I would get a different sample. So it's not necessarily a matter of turning off. It's more of you're always turning it on, you could say. And for those of you who have experience, for example, with Monte Carlo simulations, setting seed numbers is a very, very important thing to do so that you can reproduce your results in another time. We'll do some Monte Carlo simulations later in this course. Okay, so let's actually find some summary statistics for the sample that we had. I'm going to find my mu hat using call means. Covariance matrix using the co function. Correlation matrix using the core function. Okay, so this is what we get. So my mean vector is 15.29 and 20.02. So what was mu? 15 and 20. So is this do you think this is reasonable? Yeah, it's reasonable. My mu hat is close to my mu. If I were to increase the sample size, what do you think would happen? It likely, not necessarily always, because there's going to be some variation, it will likely get closer. If I took a sample size of 1 million, what do you think my mu hat would be? Probably 15 and 20. Now, why are we talking about this? Well, it's to emphasize the difference between a sample and a population. And there's going to be many instances in this class where we're worried about, let's say, sample size. And what kind of a sample size is needed for this stuff, this statistics to actually work? Well, this concept of it, the larger your sample size, the more you're getting to your expectations. Well, the larger your sample size, the more likely your statistical method will work as, let's say, advertised. Here's my sigma hat. Remember I had the variance of x1 was 1. The variance of x2 was 1.25. We're kind of close. The covariance for x1 and x2 was 0.5. Again, from this sample, we're kind of close. So let's take a look at maybe page 137. Maybe in your notes. It has this plot here. So you might remember me mentioning earlier in the class period of, well, what happens if I actually put my random sample in terms of a scatter plot, put it on top of my contour plot? What would happen? Well, this is what we get for this sample size of 20. Generally speaking, these points seem to be forming kind of an ellipse shape, kind of. Overall, is our sample size that big? No. But it's kind of show this shape that we see with our contour plot there. Again, points, they should be getting more, let's say there should be a higher intensity of points as you get towards the middle there. Of course, for this sample, we don't see anything inside of the 0.14 there. I attribute that to variability. But if I take a larger sample size, what do you think is going to happen to this plot? The points are going to be becoming more frequent as you get more towards the middle. They're going to form a closer to an ellipse shape to them. And in fact, this is what I do. Page 137, or I'm sorry, page 38, page 39. I change it, like I said, I changed my numbering system before the copy that you guys probably downloaded. So this is a sample size of 200 now, and a sample size of 2,000 as well. And you see what I just, I guess verbally said, demonstrated in these plots. What you expect to happen does. The sample is becoming more representative of the population as your sample size increases. I did find one, I was surprised by something though, and that was, for example, with a sample size of 20. Sample size of 200. This was my correlation. It actually got a little bit farther away from the true correlation of, I think it was 0.45. And again, I attribute that to variation. And in fact, I think I actually went up to a sample size of 20,000. What? Well, this is, yeah, okay, I'm sorry. So that's 2,000. And, I was a little surprised by that. So I said, okay, well, let's crank up that sample size a little bit further. And indeed, I was getting stuff that I had expected. So that is kind of surprising, even with that sample size, that would happen, that you'd be that far away. But that's what ended up happening for this particular sample. What you can try on your own is try your own seed number and see what happens. Hopefully, the reason why this happened isn't as follows. Can we actually fully randomly simulate data in a software package? It's not in terms of, let's say, a multivariate norm. Is it fully randomly generated multivariate norm? No. There are computer algorithms that are in the background that's actually doing this process. And hopefully there's not a flaw in the computer algorithm. In the past, that was a lot more of a concern with software packages. Generally speaking, I haven't seen any problems like that unless you're using Excel. So some questions then. Tell me, how would we simulate data from a trivariate norm? In other words, P equal 3. Would you use basically the same process? So if we look at this code here, what would be needed? What would we need to change in this code here? If I had a trivariate normal distribution. Yeah, the mu vector would be contain 3 elements. The sigma matrix would be 3 by 3 now. But other than that, this function, just use it exactly as before. To find the multivariate summary statistics, do it exactly as before. If you're to do plots, obviously now things are going to be a little bit more difficult to plot because you have x1 to worry about, x2 to worry about, x3 to worry about. Ooh, what about f of x if you wanted that? Now you're in 4 dimensions. There's a dissertation topic: how to plot a surface in 4 dimensions. Anyway, so why is it useful to be able to simulate data? Well, the reason is because we know the characteristics about a sample. And since we know the characteristics about what the sample should be, this allows us to evaluate how statistical methods will work in practice. And thus this leads to concepts called or not constants, but things called Monte Carlo simulation studies that help you evaluate, does the statistical method work as advertised or not? And again, we will look at that as we go along the semester. Okay, so that takes us to page 41. The temperature is 81 degrees, and it's 10:15. Why don't we just call it a day? And I'll see you next week.